Hello everyone, I'm Christian Duran. I'm going to introduce the work named ISCAS Acceleration Schemes for Low-Cost SoCs. I'm part of the Universidad Industrial de Santander WIS in the Integrated System Research Group on Chip. This is the outline for these presentations, and I'm going to start with the motivation right away. The cost of data transportation appears as the most limiting issue for accelerators' energy-efficient implementations. This is true in all areas including CNNs and security. In this example of a core, this is an example of a core designed for encryption acceleration. In the case of implementing a security system involving AES, we compose the system on chip with a processor, the ROM containing the program, different kinds of memories, and several peripherals. The lowest cost for processing is only involving the internal calculation and registers within the core. This low cost is due to the short communication paths. However, we'll still need to access the memory to bring the data to encrypt. If a heavy calculation needs to be reached, it's usually 30 times the internal calculations of addition in the loop. The access of memory is the heaviest, reaching 50 times for internal SRAM and up to 6400 times for DRAM. Our work focuses on defining an optimal architecture that reduces memory access to improve the energy efficiency. For that, we developed different strategies. First, we are going to talk about the ISCAS as a custom instruction. We designed a pipeline structure where the data in 8-bit chunks can be entered into flip-flops. From here, we use a UV calculator which performs polynomial states of the Galois field inversion. When it's complete, we pass it through the nonlinear matrix multiplication. This core, along with other versions like a one-stage pipeline and a lookup table, were included inside of a unit. This unit is included as an SBox custom instruction inside of the processor. We also use it inside of a custom AES core. We performed the instruction execution for analysis of memory access. By only accelerating the SBox, the memory access is reduced a little, but it's not significant, as the result of the SBox only reduces about 10% of the load instructions. Due to this, we implemented a DMA AES for further reduction in memory access. This is the architecture of the AES core. It includes a DMA automata to push the block for ciphering, but can be used as a standalone memory mapped AES engine. The DMA automaton is provided with a state machine for reading and writing chunks of 128 bits from the main memory. This procedure of reading and writing is monitored by several counters. With this design, the memory consumption of the core reaches down to 1.52 nanojoules in a 180 nanometer process technologies, and an optimal frequency of 3 MHz in 0.4 volts. Using the constraint instruction, the design is capable of achieving a 2 times energy reduction. A memory mapped core reaches 300 times, and the DMA inclusion makes the design to be pushed up to 900 times in the overall system on chip. If we take the performance only of the core, compared to the other works, this design reaches 2.5 times better than in performance. And finally, this design was fabricated and tested in a 180 nanometer process, including the processor with the different parts for calculating the AES. As final remarks, this work demonstrates different approaches to design an AES core for low power and low energy system on a chip. We defined the custom SBox instruction and perform analysis from the memory perspective. The DMA approach performs better for the overall SoC. We were capable to improve energy efficiency up to 900 times compared to the software and 3.5 times compared to memory mapped push-pull. Our results confirmed the opportunity to include complex algorithms for low-cost SoC for ubiquitous embedded applications. These are the references used in this presentation. Thank you very much.